So today we're going to talk about effective teaching strategies. Okay. So as I have told you last time, this is part two of my lecture. Okay. So we started with the big ideas in chemistry during our first meeting. So today I'm going to talk about effective teaching strategies. So one challenges that we have if we're teaching STEM is most of the concepts, okay, that we deal in most of the subjects are abstract. So it's difficult for our students to grasp about a given idea or to imagine what it is, okay? In some instances, some of these courses or subject involves analysis and calculations and often involving numbers. So I think, I don't know if you're going to agree with me, if it involves numbers, students have a hard time or there's a phobia that is associated with it. So maybe we can just tell our students that when we're dealing with numbers, think of it as money for them. Okay, so it's difficult for many students that are really, we could say, deficient in mathematics and statistics. And to tell you frankly, the main reason, one of the main reasons why students failed in my chemistry courses is not because of the chemistry itself, but because of the mathematics. Okay, and some colleges and university, they have to have these so-called remedial courses so that they can retrain incoming students, okay, taking STEM courses. Now, as the challenges, what we call the happen, okay, most of the courses that we have at this time, this is not a standalone subject anymore. Some of them are what we call interfaces with other fields. So there's what we call interdisciplinary courses. So most of the courses are what we call interdisciplinary. Okay, so what does it mean? You need knowledge not only in one field but in other fields. And for chemistry, as I have told you, this is a central science, so it is in one way or another connected to other courses. So it's a challenge for the students to be able to integrate some concepts that are in other courses. So usually it involves higher cognitive skills. Okay. Now, the thing that we need to do first is we have to equip ourselves with the knowledge that we teach. Okay. So how can you teach a certain course when you yourself is not knowledgeable enough to teach that given course? Okay. Now, the objective that we have, at least in the STEM courses, in teaching STEM courses, is we must be able to translate difficult concepts into understandable concepts. So the way I look at this is in simplifying things, okay? So if you're going to present these concepts or ideas in this form, okay, the students will have a hard time understanding it. So our goal is to make it in this form in such a way it's easier for them to understand. Okay, so usually our goal is to make this fruit here as enticing as the one as we have here. Okay, so what we do here is we have a complex idea, and our main goal is to simplify it. So by teaching it in a simple way, the students will have a much easier way to understand the given concept. Now, where did I get this what we call idea, or who influenced me? Maybe because it's this guy. Okay, so Albert Einstein said, if you can explain it simply, you don't understand it well enough. Now, unfortunately, the photo of this guy here is also one bad, what you could say, representation of being a scientist. So usually if you have a photo like this, they always associated science with what? Mad scientists. Okay? When in fact, you can at least put an alternative photo like this one, where he's more dashing and flamboyant compared to the one that he is here. Okay? And Einstein also said everything should be made as simple as possible, but not simpler. Okay? So I remember one of my advisors when I was in grad school, he told me that when you present an idea to another person, whether he had a scientific background or not, okay, the rule of the game is KISS. Keep it simple, student. Okay? Because simplicity is identify the essential and eliminate the rest. So what I'm going to share to you is some of the strategies that I use in my teaching career. And I think it will also be useful to you when you teach whatever course that you have. Although most of the example is chemistry, I'll try to incorporate biology and other fields as much as possible. Okay? So this is what I call as the ACE of Chem. So usually when you say ACE, okay, if you have in Major League Baseball, they have their ACE pitcher. So when you say ACE, that's your number one weapon. Okay? So for me, ACE is an acronym that I use in the strategies in teaching chemistry. So A is for analogy and archive history. C is for concept maps, cinema, and cartoons. Okay? There's another C that I'm going to tell you when we go to this example individually. And E is for everyday materials and events. And these are just some of the materials that I use. Okay? So I have the cartoon guide for chemistry. And then I have here Napoleon's Buttons, extraordinary chemistry of ordinary things, the physics of superheroes, a visual analogy guide to chemistry, and then this one, chemistry made simple. Okay? So the first thing that I have is the use of analogies. So when we're talking about analogies, it compares something abstract to something that is more concrete, which learners can relate to in their everyday experience. Okay? So when you have this analogy, there's a comparison between two things, typically for the purpose of explanation or clarification. So in these two things, one is the concept that you're trying to introduce, and the other one is an idea that is, we could say, the students know about that concept or idea. So you're trying to introduce a difficult concept by using another concept that is familiar to the students. Okay? Now, there's an advantage and disadvantage in using the analogy. So you have to know the limitations of using analogies. Effective analogies can clarify thinking, help students overcome misconception, and give ways to visualize abstract concepts. However, misleading or confusing analogies can be more than just a waste of class time. They can interfere with students' learning. Okay? Now, the use of analogies has been what we call reported as early as the time when science is new. So I'm not sure if you're familiar with this person, Johannes Kepler. Okay, so he's the one who studied about the planetary orbits. So that's around what, 16 to 1700. So he's discovered the laws of planetary motion, and he used analogies to help explain his discoveries. So this is written, okay, in one of his what we call record. So the way he wrote is, I'm much occupied with the investigation of the physical causes. My aim in this is to show that the celestial machine is to be likened not to a divine organism, but rather to a clockwork. Okay? So when you look at the clockwork, usually you have what? The numbers here, right? So the way that he tried to introduce the planetary motion is, it's just like the hands that we have here. Those are the planets that goes around the orbits. Okay, so that's how Johannes Kepler described the planetary motion. So imagine, it's been used since the early times of science. Okay, and if ever you're going to devise analogies, they say you just have to follow this rule, the FAR rule, okay, or the FAR. So you focus, okay, on a given concept. So the concept, is it difficult, unfamiliar, or abstract? And then for the students, target what ideas do the students already have about the concept? And the analog that you're going to use is it something your students are familiar with? Okay, so you use an analog that is familiar to the student to focus on the concept. So once you get the focus there, what you do is you do the action, likes and unlikes. So here you're comparing the two ideas already. So for the likes, discuss the features of the analog and the science concept. Draw similarities between them. Now for the unlikes, you discuss where analog is unlike the science concept. So here you put the limitation. You put that they're only similar until this point. Okay? Because sometimes when you teach, you just say it's just like this. Okay? But the truth is, it's not really like that. There's a limitation on it. And then you're going to reflect. So here you're going to ask yourself, was the analogy clear and useful, or the students become more confused? Okay? And then you can think of ways to improve it. So in that way, you can refocus us above in light of the outcome. So you look at the results. Was the concept become more clear, or it becomes more confusing when you use that given analogy? Okay, so this is how you develop these analogies. Now, the example that I have here, I start with the one that is practical to us. Okay, and then unfortunately for the chemistry, since that's the course that I taught, and I usually use this analogy. So here is the analogy that has been what we call commonly seen during this time of pandemic. The curve is flattening. We can stop social distancing. Okay, so you know this concept of flattening the curve, right? So you say we have it like that. So when we reach this one, we flatten the curve. So what does this mean? Okay, so the idea that they have here is, if we're going to stop social distancing, what happened is the parachute, when we start to flatten the curve, it's just like the parachute has slowed my fall, and then I can take it off now. So the way is it, unless we have 0 cases already, okay, and in that case, we have really flattened the curve to a 0 case, then at that, if you're using a parachute, you can only, okay, take it off when your feet, we could say, is already on the ground. It doesn't mean if it's slowed down, you can already take it off. Okay. Another analogy in this time of the pandemic, maybe the way that they look at this is the use of the mask. They compare it as the urine test. Okay. So if we all around naked and someone pee on you, you get wet right away because there's no mask to prevent that. So if you're wearing pants, some pee will get through, but not as much as so you are better protected. But if the guy who pees also is wearing wearing pants, the pee stays with him and you do not get wet. So this is just one way to use analogy to discuss the importance of using the mask. And the way that they put it here, the analog is what? The pants, okay? And the concept is you have to wear mask because you want to prevent the virus from spreading. So we could say the mask pertains here to the pants. The urine here pertains to the virus. Okay. Another one that we have here, 6 feet distancing. But they say this is not enough. Why? If you can smell something who is smoking more than 6 feet from you, that means the virus can also spread through that what we call distance. Since you can smell it, that means the virus can also travel at that distance. So this is just some analogy that we could say useful during this time of pandemic. Now, known analogies that we have, the eye is like a camera. Okay, so this is really, we could say, a very common analogy. And they said the camera is much better than the eye because the eye you can get blurry vision, but the camera, if you focus, it's really clear. Okay. Now the blood in vessel is like water in pipe. What's the limitation here? Usually the pipe is what? Rigid. The vessel is a little bit flexible. Okay. And then we have here the lock and key model for the enzyme. So those are the common. And then I'm going to show you a presentation. Cell is like a factory. Okay. So I'm going to look at this example. Look, not that one. So I'm trying to go to that. Presentation where cell is like a factory. So can you see the screen? Okay.
Yes, we can.
Okay. So I'm just showing you here a presentation, okay, wherein the cell is, the analog for the cell is a factory. So anatomy of the plant cell and then a given factory. So the cell membrane, okay? So here the definition here, the cell membrane is similar, okay, to the doors of the factory. In a cell, the cell membrane is part of the outer lining, and it controls what comes in and out. Like the doors of the factory allow people to enter and leave. Okay? And then the cytoplasm can be analogous to the floors of the factory. Cytoplasm is the jelly-like fluid that takes up most of the space in the cell besides the organelles. Like the floors of the factory, it's where everything happens and it takes up quite a lot of space. Okay? The nucleus. The nucleus is the chief executive officer, the CEO. The nucleus is the part of the cell that controls and directs all of the activity. Like the CEO of the factory who makes all the major decisions and is responsible for most activity. the nucleus and the CEO are clearly similar. Okay? The ribosomes are analogous to the factory workers. Ribosomes are one of the smallest organelles in the cell. They make proteins and are located on the endoplasmic reticulum. So these ribosomes are similar to the factory workers since they both create products and follow directions from the nucleus. Okay? The wrap endoplasmic reticulum, which pertains to the assembly line in a factory. So the wrap endoplasmic reticulum is where the ribosomes are located. So it's where proteins and other molecules are made. Therefore, the wrap endoplasmic reticulum is like the factory's assembly line because it's where the ribosomes make the proteins or where the workers makes the product. And then we have the Golgi bodies. It's the shipping department. The Golgi body is located near the cell membrane. It's responsible for grouping vesicles, finalizing them, and shipping them everywhere. A shipping department is like the Golgi body because it takes the final product and ships to where they need to go. Therefore, the Golgi body is like our shipping department. And then we have the mitochondria. In the factory, the corresponding mitochondria is the local power plant. In the cell, the mighty mitochondria produces energy-rich molecules like the local power plant that provides power to most parts of the factory. The mitochondria powers and produces energy in the cell. Okay? The lysosomes is similar to the maintenance crew. In a cell, the lysosomes are responsible for breaking waste down and handle the movement of trash and waste. Therefore, lysosomes are like the maintenance crew or janitors because both handle waste and general trash. And then we have the vacuole, which in the factory is the storage area. So the large central vacuole is one of the cell's biggest organelles. It stores waters and nutrients. This is very similar to the way the factory storage closet stores tools, machines, and other supplies. And then you have a cell wall, okay, in the plant cell. So in the factory, that's also the wall of the factory, the structure of the walls of the factory. So the cell wall is the outermost lining of the cell. It's found only in plant cell, okay? There's no cell wall in the animal cell. It protects the cell and maintains its shape. Like the cell wall, the walls of the factory protect the factory workers, protection and maintain the building structure. And then we have the chloroplast, which in the factory is the solar powered rooftop. It's not only the rooftop, we have to put the solar powered, okay? Because the chloroplast, we could say, since the plant don't eat food, they use the chloroplast to transform energy they absorb. So they're the one who gathered the energy and then transform it, okay? So they transform energy they absorb from the sun for the cell to use in a process called photosynthesis. Since the solar power panels absorb light from the sun and transform the energy to power the factory, the chloroplast and the solar powered rooftop of the factory are very analogous to each other. So they really need to put the term solar powered so that the function will be similar to the chloroplast. And this scenario, which they call the homeostasis scenario, So the cell, the vacuole is too full of water and nutrients, so that's a problem in the cell. In the factory, the storage area is overflowing with tools and other supplies. So what's the solution in both of them? So the vacuole stops taking in water and the other organelles take the water when needed. Once the vacuole isn't at maximum capacity, the cell can start absorbing water again. In a factory, production is put on hold until most of the supplies are shipped out or used. Production can then be resumed because there is space in the storage area. Okay, so those are what we call a very good analogy of a plant cell with a factory. So I think that's the what we call longest analogy that I will give you today. Although I still give you other analogies that we have. Okay, so what other analogies that I can give you? So here, these are stuff that I use in my general chemistry courses. So the first set of analogies that we have here is the way I discuss the three physical states. Okay, solid, liquid, and gas. So usually, the simplest way to differentiate the three is just by looking at their shape and volume. So solid would have a definite shape and a definite volume. Liquid would have a definite volume but not definite shape. While gas has no definite volume and no definite shape. So one way to compare or to use analogies aside from the one given here is usually when you hold a typical face-to-face class, students are seated, okay, in a regular arrangement. So that's, we could say, the solid. The students are in the liquid phase when they are in the building or in the school, okay? There's much distances between the students, just like the molecules in the liquid. And the students are in the gas form if they are in their own residence or in their home, okay? Because they're far away from one another, just like the gas. So the way that I put here, the so-called pictorial analogies. So these are the series of articles that came out in Journal Chemical Education. So Professor J. Fortman describes solid like a military unit, small distances between molecules. It's rigid, they are all in order, and there's no random motion. Okay? Liquids, he described it in terms of reunion party. There's small distances between molecules. There's some flowing of the people in a reunion party. There's a little bit of disorder and then some random motion. Okay? Now for the gases, he described it as a soccer game. Okay? There's a distances between molecules. There's diffusion, much disorder compared to the liquid, and much random motion. So that's the first set of analogies that he described. Now the next set of analogies that he described is when we discuss this so-called type of solids. So in the type of solids, okay, there are four types: molecular, ionic, macromolecular, solids, and metals. So how are they differ? Usually they differ in their properties because of the forces that hold them together and because of the units that they have. So what they have here is in terms of the units that they have. So molecular solids, he described them as coupled. Just like water, it is made up of what? Hydrogen atom and oxygen atom. So molecular solids, they are what we call held by intermolecular forces of attraction, like hydrogen bonding, dipole-dipole interaction, or London dispersion forces. Now, ionic solids, on the other hand, they are made up of ions. And here, Professor Portman described ions as men and women. The units are cations and anions. So cations are positively charged, anions are negatively charged. So if you have ionic solids like NaCl, okay, so usually it's made up of a negative chloride and a positive sodium. And the way he described this is either the men are the cations or the women are the cations, and the anions are the other party. Okay. Now for the macromolecular solids, so these are the one that is being held by covalent bond, either atoms or set of atoms. So for instance, carbon in the form of graphite or allotropes, they're just made up of what? Carbon atom. Now, why they have the different what we call properties? The way the carbons are connected to one another. Okay, so in some instances, carbon in diamond is so what? Hard, because they have this arrangement of tetrahedral arrangement, giving them a rigid property. Diamond being what? The hardest chemical or the hardest substance according to Moscow. Graphite, on the other hand, they are arranged in layers, so graphite is usually soft. That's your pencil lead. Okay, so this is how Professor Portman describes macromolecular solids. All units are bonded together. Now, example of those that is made up of more than one atom, we have the silicon oxide. Okay, the expensive term for this is what? Quartz. The cheap term for this is sun. Okay, so what happened here? If in the diamond and graphite, these are all C. In SiO, this is an Si, this is an O, this is an Si, this is an O. That's that kind of arrangement. Now, the last form of solid is the so-called metal. So metals are known as what? Good conductors of heat and electricity. So the units are the same atom, okay, cation with the so-called mobile electron. So usually you have this so-called sea of electrons that allows metals to be good conductor of heat and electricity. So that's how the pictorial analogies was being what we call presented. Then other way that we could say useful here is the concept of heat. Okay. So if you're going to look at the concept of heat, how do we describe heat? Okay. So here we put an analog of heat to money. When someone gets rich, usually what? Because you get money. And when something gets hot, usually it happens because you gain heat. Okay? And when someone gets poor, usually because you lose money. But when something gets cold, it means you lose heat. It doesn't mean you gain coldness, right? Because in the first place, we call it heat. So when we say heat, it's usually a concept that we use when an object becomes warm. And the way that the heat is transferred is usually from what? From warm object to cold object. So when an object becomes cold, it's not because it gains coldness. Okay, it becomes cold because it lost heat. Okay, so that's the way that Professor Portman describes the concept of heat transfer, and then the difference between thermodynamics and kinetics. So what's the question that is associated in thermodynamics? So usually thermodynamic question is similar to will a reaction occur? Okay. If the answer is yes, that's the only time you will have a kinetic question. If the answer is no, then there's no kinetic question. Okay. So the way that we look at this in terms of thermodynamics and kinetic is the height versus the path. Okay. So for the reaction to happen, you should overcome the so-called activation energy. Now, if the answer to the question, if the will the reaction happen is yes, then the next question is what? How fast the reaction will be. So that now pertains to what? The path. What path length are you going to take to reach the reaction or to complete the given reaction? Okay. Will it be using an airplane, which is what? Faster than, let's say, riding in a bike, what we call driving a car. Okay, so that's how this pictorial analogies tells us. And the last picture that we have here is entropy. So entropy, as I told you, this is what? A degree of disorderliness or the so-called randomness. So what is the second law about the entropy of the universe is increasing. Okay, so what does it tells us? Which will happen spontaneously, a system that becomes more disordered or a system that becomes more ordered. So based on here, it says here, it takes energy to create order. Remember when you're a child, usually it's easy for you to what? To make mess of your room. Then to fix it. Fixing it usually means putting everything in order. But the universe is towards the one wherein there is more disorder. Just like look at world history. There are longer times when nations are at war than at peace. Because that's the name of the game. Chaos, disorderliness, that's entropy. Now, the next one that I have here, this is something to do with the quantum numbers. So quantum numbers is used in quantum mechanical model to describe the orbitals of a given electron. Okay, so I told you they're all S, the size, the shape, and to give you the S here, it's the spatial orientation. So size quantum number, which is N, it just tells you how big your house is. N is equals to 2 is much bigger than N equals to 1. Now L pertains to the shape. So you have heard the S, P, D, and F. Okay? So the one that they say, the S, P, D, and F, that is associated to whatever L value that you have. S is given to 0, P to 1, D to 2, and F to 3. L value. Okay? And one student would explain that to me, S is equals to spherical, P is peanut, D is double peanut, and F is flowers. Because if you're going to look at the shape, those are the best description that my students explained to me one time. M sub L has something to do with the orientation. Okay? And the value of M sub L depends on L. So usually N is equals to 1 to infinity. L would be from 0 to N minus 1. And M sub L value would be equals to negative L to positive L, including 0. Now, this one pertains to the so-called delocalized and localized electron. Okay? So in chemistry, you have this concept of bonding and non-bonding pairs. So non-bonding pairs, that's your lone pair. And they said if you have a lone pair, you have a delocalized electron. So they what we call describes your electron there as the horse. So in a localized electron, like a bonding pair, that's the only place where the horse is. But in the localized electrons, your what we call horse can move around. Just like what happened to the lone pairs, your electrons can move around. Okay? That's the concept that is being described in this analogy. And then other stuff here, like what's the difference between empirical formula, which is the simplest ratio, molecular formula, the actual number of atoms in a given molecule, and the structural formula. That's how your atoms are being arranged. Okay? So the way that they look at this in terms of machine and class. So if it's the empirical formula, the machine is the number of 3 gears for every 2 springs. For class, 2 males for every 1 female. Molecular formula, the actual number in one machine, there's 24 gears for every 16 spring. If you're going to simplify this, that's your empirical formula. So here in class, there's 80 males for every 40 males. And if you're going to look at the structural formula, that's how your gears and springs are arranged, the blueprint. In a class, that's the seating arrangement. Now, you also have the so-called structural isomers. So what's this structural isomers? They have the same formula, but different arrangement, just like this one. So this is one isomer, and this is another isomer. So if we can put it like this, and this one we can put like this. But all of them has the same what? Number of person, just like this one. They have the same number of carbon and hydrogen. You can also use analogy to describe electrolyte. So this is just a nuts and bolts thing. Okay? So when you say non-electrolytes, all of them are molecules. When you say strong electrolytes, your nuts and bolts separated like ions. And if it's weak electrolyte, some of the nuts and bolts were separated. Okay? And then another thing that I use is when I describe the atomic size, I use the what we call the balls. Okay? So from ping pong to basketball. So there's a saying in the government, okay, the higher your position, the smaller the balls that you play for the sports, right? So most of the presidents, they like to what? Play golf. The golf, I think, is the same size with the ping pong. Okay? And the sports that I use here, the contact sports, I use this for collision theory. How do atoms collide? Or when does reaction takes place? Reaction takes place if there's collision. The same with contact sports. Okay? You can only score points here in judo if you pin down your opponent. Here in wrestling, if you pin down your opponent. Now, what does this hockey means here? I'm not sure if you're familiar with the Le Chatellier's principle or the so-called stress. Now, in hockey, usually you have what? 5 versus 5 players with the goalie. Now, there are times when there's a stress. So when is the stress? When you have this so-called power play, or in the opponent, you have this what we call penalty. So when that happens, it will become 5 versus 4 or 5 versus 3. So that system is under stress. Okay? And it will go back to equilibrium when the penalty is over or when someone scores, leading to the penalty being over. And then, since I'm teaching higher chemistry, I try to describe this what we call chromatography, which we're going to discuss a little bit next meeting. So this is the separation process. So you're going to inject something, and what will happen, they will separate into their components like this. So the question is, what's the basis of their separation? So I try to use sports and nature. So in the sports, try to use swimming or board sailing, wherein there's a separation between the competitors. The same thing that happens during the separation process. Or I try to compare it with the bees and the wasps. And when they pass through flowers, which one will stay longer in the flowers? Usually the bees. The wasp will just go pass through the flowers. So in that case, there's what we call the separation that happens. Other analogies that they have, this is where accuracy and precision. And this has something to do in the so-called activation energy. And this is something to do with the strong acids and bases, because acid is one wherein it donates hydrogen. Base is the one that accepts hydrogen. Okay, so how good are you as a pitcher or a quarterback is how efficient are you in delivering the ball to the receiver, just like a strong acid. Now, this one is something to do with the limiting reactant and exact reactant concept. Okay? Now, another analogy is the resonance. So what do you think if I breed donkey and horse, what is the end result? Anyone?
Mule.
A mule. Okay? Because how do we describe this, what we call resonance? So resonance, they have more than one Lewis structure, okay? But the exact Lewis structure is neither of the written structure, but the average of the two structures. Now, what do you think is the result when I combine dragon and unicorn? Because usually, if we write the Lewis structure of a resonance, we put there two or more. But they don't really exist, just like the dragon and the unicorn. Okay? The exact Lewis structure is just the average of those written Lewis structures. So which do you think animal exists when you combine dragon and unicorn? Anyone? What animal can result if you combine a dragon and a unicorn? Both of these are what? Fairy tales. They don't exist. Okay? You combine them, you're going to have what? Any guess? A dracorn? Any guess? Ta-da! Anyone? Before I show the result? A very cranky horse? A rhino. Now you might say, why Pegasus? No? Why? So this one was obtained from the unicorn, and the scales was obtained from the dragon. So remember, when I told you resonance, the correct Lewis structure is the one that exists, okay? But the one that is written, that's not the correct Lewis structure, because the correct Lewis structure is the average or the hybrid of those two. It only exists in paper. Just like dragon and unicorn, they just exist in paper. The one that exists in real life is rhino. Okay? Now, I also have an organic chemistry here. I'm not sure if you're familiar with the SN1 and the SN2 mechanism. Okay? So what's the difference between the two? One of them would undergo a transformation wherein the reactant is very different from the product. Just like a worm turning into a caterpillar turning into a butterfly. Now, the other mode of reaction is you can see both the reactants and the products in the intermediate or transition state. Just like this what? Tadpoles, okay? Transforming into a product. So that's the SN1 and SN2 reaction mechanism. Okay? So those are just the different analogies. And you can use them, maybe if you're in the bio, there are some bio things also that are available online. Okay? Now, the next step that I have is the so-called archive history. So I usually use here the chemistry. So since time immemorial, they already have the so-called 7 metals of antiquity. And these are metals associated to, let's say, a particular planet, and they say a particular day, because there are 7 days, okay, of the week. So gold, silver, iron, copper, lead, tin, and mercury. So what does it mean? These metals is already known since time immemorial. Okay? And I don't know if you're going to look at the world history, they usually has this so-called age that is after what? Metal. So we have a metal ages timeline, the copper age, the bronze age, the iron age, okay? Before that, we have the stone age, the bronze age, the iron age, and these are the timeline that they have. And then when matter, or when they try to describe the materials around them, Aristotle suggests that all materials are either made up of these 4 elements, right? So what does it mean? Any wet material is a combination of air and water element. Any cold material is a combination of water and earth element. Any dry material is a combination of what? Earth and fire element. And any hot material is a result of a combination of an air and fire element. So maybe you're familiar, I don't know how old are you. When I was a kid, we have this so-called Captain Planet. Captain Planet came out when you combine the 4 elements. Or maybe if you're a little bit younger, you're familiar with him, the Avatar. Okay? So he's what? An airbender. Okay? So I included it in archive history because that's the concept that the Greeks accepted. Although Democritus already give the idea that all materials are made up of atoms. But the problem with the Greeks is all of them are what? Speculation. There is no scientific evidence. There's no experimentation. Everything is just speculation. Okay? So that's how Greek philosophy, so it's more on philosophy compared to science. I think Dr. Demos discussed that concept to you because he's a Greek. Now, the Napoleon Buttons, I would suggest if you are a chemistry teacher, maybe find a copy of it online. Sometimes the PDF are available. So it's a very good, we could say, book wherein the authors describe 17 molecules. So how 17 molecules change history? Because the problem, I think, with students not liking these science courses that we have is they cannot find relationship of these courses in real life. But if you can tell story of people on how they live and how they discover the scientific discoveries or accomplishment that they have, okay, the students can relate themselves to this one. So they just titled it as Napoleon's Buttons based on the slides that I'm going to show you later on. But these are the 17 molecules that he discussed on how these molecules shape history. Okay, so the first chapter that they have there is what? Peppers, nutmeg, and cloves. In short, there are what? Spices. And then ascorbic acid, what it is? Vitamin C. Now those two are related because during the 15th century, you have the so-called exploration age. Okay, so during this exploration age, which are the superpower? You have the Spain, Portugal, maybe UK. So usually they explore, okay, the world to find what? Spices. I don't know if you know the story how the Native Americans are now known as Indians, for the American Indians. They said that when Columbus landed on America, he thought he landed on India, and he called the people he saw Indians. Okay? Because what Christopher Columbus was trying to find is an alternative route westward. But what he found out is the Americans continent. And the story that I have here is this one. This is the story of this exploration age. So this is Ferdinand Magellan. So Ferdinand Magellan, he's a Portuguese, but Spain gave him 5 ships. And his main objective is to find the Spice Island, which is Moluccas. And what did he do? He traveled way west, and then he passed through the Strait of Magellan, so the American continent, and then he got to the Pacific Ocean, and then until he said he discovered my country called the Philippines. But Philippines is already existing before he arrived there. And during his voyage, only one ship got back to Spain. He was killed by my countrymen. Okay, so it has something to do with finding these spices from the east. Now, one of the spices that they have is the so-called nutmeg. I don't know if you're familiar with nutmeg. It's a very, we could say, in-demand spices during that time, to the point that the Dutch is willing to give up what? New York City to the Englishman. Okay? New York City used to be what? They call it New Amsterdam. So what happened? So the Dutch are controlling the what we call the market of nutmeg. So the English people is willing, okay, to the Dutch people is willing to give up New York, okay, which is New Amsterdam during that time, if the English is willing to give one of the islands in the east that contains the nutmeg. Okay, because one of the things that comes out there is isoeugenol, which is the structure there. So until the Second World War, the Dutch people controlled the market of nutmeg. So if the Dutch didn't give up the place that becomes what we are now, New York, we're going to be called New Amsterdam. And maybe our language right now here is Dutch. Okay. So New York, if it stays with what we call the Dutch people, we're going to be called the Orange County, right? Because the Dutch people are known as the Orange, right? The Orange people. If you watch the soccer, they always have orange jersey in them. So that's the story of New York. Okay, how the Dutch people give them up since the Englishman is willing to trade it for another island that contains the nutmeg. Now, the story of what we call Napoleon Buttons that I have told you before is, when did Napoleon's problem started? And that's also the time when Hitler started to have problem. Okay, it started when he went to Russia, right? So Russia, Russia, Russia. Until now, it's still a problem. Look, Donald Trump problem is also Russia. Okay. So what happened when Napoleon went there? The same thing with Hitler. Okay. He was met with winter. So when I say Napoleon, it's the person, not the alcoholic drinks, because there's a Napoleon brandy that I don't know if it's popular here. Okay. So what's the story of the so-called Napoleon buttons? So buttons during that time is made up of what? Right now, a button is made up of what? Plastic, right? If you're going to look here, I have a button here. It's made up of plastic. But during that time, it's made up of a metal. And that metal is known as tin. So you could see some grenadiers. There's a lot of buttons that they have in their shirt. Now, what's the problem? If Napoleon won his battles in Giza with science, he lost his campaign in Russia also with chemistry. Why? Because tin has two forms. They have the stable tin and the unstable tin. And what separates the two? Temperature. At low temperature, okay, your tin disintegrates. So what happened? Anything that holds your clothing together will just fall apart. So his soldiers during that time is what? Trying to keep themselves more warm than concentrating on the battle. So what's the Russians? The Russians are used to the winter, just like what happened in the Second World War. They took advantage of that. Okay? So historians said of the 700,000 that Napoleon went in the campaign, only around 20,000 went out alive. And until the present, they can still find mass graves of those soldiers that was killed due to the winter. That's the winter of, I think, 1810 or 1812, okay? Because the Russian campaigns influenced Peter Tchaikovsky to write a musical about it, the War of 1812, some sort of that. Okay, but that's how we could say chemistry during that time. They didn't find out that tin has two forms, the stable form and the unstable form. And for them to disintegrate, you need what? 12 degrees Celsius. And the Russian winter is much lower than that. Okay, so that's the introductory part of the Napoleon's button. So we're done with our letter A. So let's go now with our letter C, concept maps. So these are just graphical tools that's used to organize and represent an individual's knowledge by creating a relationship between concepts in the forms of propositions. It's an ideal tool to assess the depth and breadth of students' knowledge structure. And it's indicate how students organize information into their knowledge structure. So allow us to visualize how students relate various concepts to each other. So here in the concept map, you're trying to relate one concept with another concept. And this is one of the best assessment material that you can use to see if the students understand. Okay? Now, in a concept map, there are three components: the concept terms, the linking arrows, and the linking phrase. So the concept terms, the linking arrow, and the linking phrases. Okay? So if you're going to look at these concept terms, the, the linking arrows is the one that provides relationship between the two concepts. So concept map here and then two important components. Okay, so the linking arrow is the one that will provide the relationship. Now the phrase there, like this one, contains, that's your linking phrases. So it represents the relationship between a pair of concepts. So a concept map can be used to organize information such as vocabulary, ideas, or it contains two important components. One is major topic, the other is linking words. So like this one. And the example that I have here is this. Trees provide oxygen, which is needed by most living organisms. So you were able to relate living organism with trees. For those who are in the so-called living environment, okay, or biology. I asked my wife what it is, and he said, no, it's biology. Trees also provide shade. And then trees are used to make paper, which can be used to make what? Notepads or books. Okay, so that's a very what we call simple concept map. At least trying to relate trees with oxygen, paper, books, or living organism. You can also have a concept map like this. Concept map represent organized knowledge, or concept map help to answer focused question. Okay, the organized knowledge should include past associated feelings or affect add to a given concept. So this is, you become more a little bit complex. So here, this is just a concept maps wherein you can relate different concepts in chemistry. You can start with the solution that can be described in terms of the different concentration units, which is dependent on the colligative properties. And among these colligative properties are this one. Now, in one of the solutions there, you will be associated with the molar mass, which can be related to the gas law. Now, the molar mass can also be related to the formulas and indirectly to the equations. Or you can do it like this. The particles nature of matter. So you have here solid, liquids, and gas, which you can describe in terms of common elements. So the particle nature, the chemical elements, so everything goes to atoms. So in the atoms, you have the chemical bonds, where one of them is a covalent bond. And the chemical elements can also be related on a periodic table, wherein you have there the different name, symbols, period, and then you can classify it as metals, non-metals, or metalloids. And in the atoms also, you have there the nucleus, electrons, and then the concept of the isotope. Okay, the same number of proton, but different number of neutron. So these are what we call example of concept maps. Now, the other C that I have is cinema, but I call it entertainment. Okay, it's just a combination of chemistry and entertainment. So it happens to me because they gave me a class that is off season, and the schedule is just once a week at evening from 5:30 to 8:30. So how will I make my students alive or at least engage during that time? Okay, so what I do here, which I'm going to show you, is I use video clips from movies, television series, and YouTube to enhance the teaching and the learning experience of an introductory chemistry lecture class. So I try to, I'll try to show you some example that I have here. So in my Blackboard, I don't know when our Blackboard will come, I have this part that says entertainment. And in that, what we call portion, I put there's some videos that we have here. And I try to put some clips here. Some of them are still available, some of them are not, because I don't know. So do you see the YouTube?
This is what you are going to learn to do in my class. If you do not care about this class, then neither do I. If you do not participate and show up with enough sleep to make it through the 55 minutes, 3 dawns a week that I have to be here, then you do not care about Speech 217, the art of informal remarks. So get out. Get out now. Go. Right now. Go!
So maybe this is a clip that I got from, I forgot, Larry Crown, I think. That's the title that we have. Okay. And then another one.
An ephemeral language, contracts, quality differentials, pressure trends, the intangible.
Just wait. I just tried to fix the thing. So this is the rule. I think you also have a problem with your students.
An ephemeral language, contracts, quality differentials, pressure trends, the intangible elements of the individual value index. Subtle interpretation is required, as is full concentration. Your device, please. They call them smartphones, but only dummies use them in my class. Let us begin with the quality.
So just wait. I'm just trying to find. Yeah. So I usually give them during this what we call first day of class, because I think even you has what we call problems with the smartphones rule. I don't know how you do it in the high school, but for us in the college, usually I cannot do anything, because if you have a large class and those behind the back, whenever they stoop down and they're laughing, you know they're doing something. And mostly it involves their so-called smartphones. Okay. So I give them, but the one that I usually give them, it's a subtitle thing. I try to see. I'll go to this one here. And then I'm going to put there.
Professor, with the smartphones, I think we should find a way to incorporate it into our classes.
That's the only one that I found a thing that is, we could say, relatable to them. But since I do it in the beginning of the class, sometimes they just forget about it. I have here
นเขามีบ่อน้ำศักดิ์สิทธิ์
Just look at
ตำนาน
the
เล่าว่า ผู้ใดแบกน้ำขึ้นไปเติมให้เต็ม เทพเจ้าจะปรากฏมามอบพรวิเศษ
อยู่ไหนอะเทพเจ้าอะ
yeah. So I always what we call show it to them at the beginning. And some of them was able to pick the message. Okay. Some of them just don't have an idea what we're talking about. So if you're able to what we call get the message to that, okay, is whenever you study something, you just focus on what you do. Okay, because most of our students are what we call grade conscious at this time. So the way I ask them to do is every time we meet on class, try to learn something about the topic that I discussed, and the grade will just come easier to that. Okay, because one thing I always explain to them when we have in class, in this course, everything is on them. It's not me. I'm not their enemy. Their enemy is their own self. Okay? Because the way I try to incorporate to them the course, I don't know. I'm trying to share this thing. Slideshow. Why is it not doing anything? Also the storage. So the way I try to do it is this course is just the letter itself, like this. So sorry if you're not chemistry, but it only works if it's chemistry, or else if the students want it their way, those letters can rearrange themselves, and at the end of the semester, they might say this term. So if you're going to look at this, those letters came from the chemistry. Okay, so usually that's how I ask my student to at least how they need to form for the what we call for the course that we have. Because if they're not going to do that, most likely they're not going to do well in our course. Okay, so those are just some. Okay, and that's just in terms of the implementation. I also have what we call stuff that is related, we could say, to the materials itself that is being taught. Okay, so I put here some, we could say, non-chemistry, but I have some chemistry stuff there. We have. So we have here this one. So this is a clip from a James Bond film. So if you're on the mat, oh, I hope it plays. If it doesn't play, then I can just give you the links, but I don't have the link because this is a personal file. Media not found. Oops, not too good. But the thing that they have there is this one. So it's 106 miles from the terminal going 70 miles an hour. And then one of them said, we have 78 minutes. So somewhere along there, the math is not good. Okay. Or we can have this one. I don't know if the clip will play.
PhD. PhD? That's Doctor of Thinkology. The sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side.
So if you're in the math, I don't know, that's how you define isosceles triangle. The sum of the square roots of two sides of an isosceles triangle is equals to the square root of the remaining side, because I think the notion that is being described there is a right triangle. Okay? And you can take advantage of these so-called groups in the what we call movies. There's a lot of these groups that they have. It's not only the one that I have what we call shown to you there. And I try to say, what's wrong with this one? Okay. And I think the one thing that I really want to describe here is, I don't know if you're familiar, if you know Indiana Jones. So I try to look at the clip of Indiana Jones and show to you, okay, how he was not able to do math very well, not math, but chemistry very well. So Indiana Jones. This is still a commercial. So once the commercial is done, I'm going to show you the clips.
Classmates, show your school pride.
So do you see the Indiana Jones scene now?
Vamos, Javi. There is nothing to fear here.
We'll go away right away. So right away there, you can say, what's the concept that is being shown here indirectly? Okay, why did Indy, what we call failed Gen Chem for that? He replaced the gold statue with sun. Okay, the only one that is the same is not the what we call the mass. Because if the mass is the same, that will not happen. So the only one that's the same is the volume. They have the same volume as the what we call golden statue and the sandbag that he replaced them. But the density is different, so the mass is different. So that's an in-depth learning that you have there. But some students said, oh, what is it all about? What is it all about? So you will see right away if the students get the concept that you discuss or not. I have an example on that. What we call the paper that I have emailed to you. I'm the one who wrote the thing. So if you don't want spoilers, don't read it, especially in Game of Thrones, because I have discussed something there about the Game of Thrones. So if you have not seen Game of Thrones, don't read it, okay? It's just that I'm trying to find ways at least to keep them at least engaged. So every meeting, there's at least one film clip that is related to the topic that we discuss. Okay, and I think you can consider, because as of now, most of the students are what? They always have this smartphone. So if you have some video clips that can make them more interested in your class, then that would be better. That would be much, much better. So if we're going to continue, if you're fan of cartoons, you can find a PDF copy of this, The Physics of Superheroes. This is already in 2nd edition right now. So it's just telling you about the superpowers that these superheroes look at them. So look at the real and the fake side of the comic book universe. It's either DC or Marvel comics that you have. And it can discuss there that some of the physics seen in comics book is correct. Some of it is just plain wrong. Some are not as easy to answer as it may depend on still developing theories. But the book provides an engaging and witty commentary while introducing the ordinary reader to both classical and cutting-edge concepts of physics, such as Superman's strength can tell us about the Newtonian physics of the force, mass, and acceleration. Villains like Electro and Magneto tell us about electricity and magnetism and others. Okay, so here in that one panel, it shows there how Superman launches himself up almost along the side of the building in a great leap. And then another thing that I use in cartoons is I found this thing when I was teaching. I was a new teacher during the time, I think around 1999. They say here, heaven is hotter than hell. Okay? And they use some phrase in the Bible to describe the condition of heaven and hell. And from them, they use known scientific concepts to get at least an idea on the temperature of the what we call heaven and hell. So they try to look at here, the temperature of heaven is around 525 based on the entry there. Moreover, the light of the moon shall be as the light of the sun, and as the light of the sun shall be sevenfold as the light of 7 days. Okay? And then the temperature of hell is described in the Bible, but the people not believing shall have their part in the lake which burn with fire and brimstone. So 525 verses 445, so we can say hell freezes over. Okay? But you have to be careful on that, especially if you have some Christian student. But as I've told you, this is just what we call trying to make your mind, make your students' mind critical. Okay? And then I use cartoons to describe the so-called Krebs cycle, how the different reaction in that cycle happens. And then this is a simple one. I got this from the pictorial analogy book. So how they differentiate the two bonds, covalent and ionic bonds. So in terms of properties, low melting point and boiling point, high melting point and boiling point, and then sulfur and squisher, harder and inflexible, more flammable for covalent bond, less flammable here, not soluble in water, soluble in water, and last, conducts electricity in water. And then in one of my high course, analytical chemistry, I tried to explain electricity in terms of the bolt pushing the current, which is being what? Stopped by resistance. Okay, so this is the potential that pushes the current, and then this is the resistance. So if you're going to look at the words that they have there, the volt, the amp, and the ohms, that's the unit. Then I also use this so-called everyday material. So at least students can relate what they're studying in the course to everyday life. Okay? So whenever I have this example, I usually use the cooking because they said chemistry is like cooking. You just don't lick the spoon. Okay? So I use the stew, the soup. So I ask them when I discuss boiling point elevation, why is the boiling stops when you add salt? So what happened there? The solution just becomes has a much higher boiling point. Okay, so it will just starts to boil when you add more heat on it. And then for the French fries example, I asked them when you're frying the French fries or the potato, which boils first, the oil or the water in the potato? And in terms of boiling egg, I don't know if you notice it, if you heat any material, most of the materials will become soft. But for the egg, it will become hard. Have you noticed that? Okay. It's only the egg that becomes hard, but the rest, whenever you heat it, it becomes what we call soap. And then during this time, I asked them to do home experiments. So I use Coke. Okay. And I usually say Coke, chemistry, okay, experiment. So I asked them, what happened if you soak egg in soda? And there's an alternative for that. You can soak egg in vinegar, but you don't like the smell of the vinegar, right? So you prepare the soda. So after several days, I asked them to what we call observe, because there's a reaction between the eggshell and the acid. So there will come a time that if the acid is strong enough, you're going to lose the what we call the calcium component there of your eggshell. It will react with the acid. And then I asked them to compare the diet and the regular soda. They do evaporation. So as what we call notice at the end, there's more sugar in the regular one compared to the diet or the Coke Zero. So as we say, regular soda, it has full of sugars. That's why I think the main problem that they have is diabetes. That's why when the cases of diabetes went up, what the Coca-Cola company do is they introduce the diet and the Coke Zero. But what did they found out with the diet soda? It still causes diabetes, right? So the diet there just means die with T, diet, okay? Diet soda still kills you, okay? The same thing as the regular one. Now, I asked them, although this is not really as the one that we get shown here. So I asked them to add milk with soda. So what we see is just a cloudy white solution, not the one the same as this one. Maybe it will make it longer, then we will see it. But what happened here is there is a reaction between the phosphate here and some materials in your milk. And that results to the discoloration of your soda and formation of some precipitate. And then this one is a different, what we call type of milk. So in almond and the coconut, you still see the color there. And then this one, the controversial one, when you add Coke with bleach. So the idea there, don't drink the mixture, okay? Although President Trump said you can drink disinfectant for COVID, but don't do it because it will kill you, okay? But the idea that we have here is what we call, why do we use bleach? Bleach usually oxidize some materials, and in that oxidation, it becomes white. That's why most of the bleach, if you do your laundry, you use only it in white stuff, okay? So in white stuff, in this thing, it's doing the same stuff. It's removing the color, okay? Because bleach is a good oxidizer. It's a good oxidizing agent, okay? Don't give this as home experiment because you don't know what they will do. And then the simplest one, if you have a big container there, all you need to do is put those cooking. Of course, they should be full, not empty, okay? If it's empty, it will be not like that. So you can compare a diet a Coke Zero, a diet Coke, or a regular Coke in can. So you will see the regular soda, the regular Coke will just go down, or at least the diet or the Coke Zero is a little bit floating compared to the regular one. Now the last one, which I don't ask them to do because this is messy. I know you have seen about this, is the Coke and the Mentos experiment. If they're going to do this at home, it will be a mess at your place. So don't do it at home, okay? If they have an open space, the more Mentos that you have, the more we could say, how do you do the more messier it is. Okay, there's something in the Mentos that reacts with the Coke that produce this one. So they produce a high pressure, some gases here. So there's a site that's called Compound Interest, and they discuss about the everyday materials. It's a very good source of what we call information. And the way that they put it there is communicate. Okay, so they always have the chemistry of stuff. So here the example is just the chemistry of decaffeinated coffee. So you can go to their website. I think they were able to publish a book already with just a compilation of that thing. And then you can also include some trivia information like this one. So this is just the same species. The only difference is what? Okay. The only difference is depending on your soil. If your soil is acidic, it becomes what we call blue. If your soil is basic, it becomes red, which is usually the reverse of our usual litmus paper, right? And red litmus paper is in acidic solution. Blue litmus paper is in the what we call blue litmus paper. Now I just found it in what we call some Facebook posts, but remember, not all posts in Facebook are true. Okay, because I'm going to show you some stuff here that I also got from these so-called memes, like this one. So what can you say about this carbon-free sugar? Is that true? It's written there, carbon-free here. But we know sugar is made up of this, or in some, I'm not sure, but I know this one. The other one is a C11H22O11, I think, or O12, the fructose one. Okay, but there's no such thing as carbon-free sugar. Okay, and then this one in the news. So this is what Jeff Glore. So carbon monoxide death. So what's the problem with that one? If it's a carbon monoxide, it should be like this one. Okay, and then this one. So rust, this is rust. It's called, it is caused by, it's called oxidation. It's caused by oxygen. We breathe oxygen every day. It can do this to a metal pipe. Imagine what it can do to your lungs and health. Sure to help raise awareness about the dangers of oxygen. You have a lot of stuff like that, right? That's why I told you the sources of Facebook is you have to what we call look at it carefully. Okay, so if dihydrogen monoxide can rust these pipes, just imagine what's going to your insides. And then now we have the question to the, we now have the answer to the question, which comes first, the chicken or the egg? So scientists finally concluded that the chicken came first, not the egg, because the protein which makes the eggshell is only produced by the hen. So it's always have this chicken egg question, okay? Or you can use events like the deflate gate. So what's the problem on that? I don't know if the Patriots fan will like it, but there was some what we call pressure reduction that happened in the what we call the bowls that's used by Brady. It's not because the temperature is too low, and they found out by calculation, even the temperature is too low, the pressure of the ball should not be as low as that one. Okay, so it's a very good opening topic question to engage the students. So some stuff that you could do is how caffeine and chocolate are what? So different, but they're just what? One methyl apart. So these are just some of the stuff that you can use, okay, to at least bring more excitement and make your students more engaging in class. So what will I ask you to do for this part? Okay. So what I will ask you is maybe using your own course, because not all of you are chemistry. I will accept even if it's biology. This is the thing. You're going to develop a material that you're going to use in your class so that you're preparing it for a course requirement, and at the same time, you're going to prepare it as a teaching material for yourself, right? So it's just one preparation for two purposes, okay? So give me at least two examples, whether it is analogy or movie, that you're going to use your own material, okay, using the strategies that I discussed. It's up to you. I'm not going to what we call the limit you on the choices, but I would prefer, if you're teaching biology or living environment, use materials from that course. Okay? You can follow the example that I use, or you can make it more specific. If you make it more details, like the cell and the factory, that's just too much. But if you want it like that, because this is the thing, you're going to use it in your class. Because I don't want to be an additional burden to you. Okay? So as much as possible, all the materials that you will submit to me, I want it to be useful for yourself also. So I don't need it to be chemistry, because I found out I think only 5 of you are really chemistry.
Hey, Professor, any update on when the lecture is going to be available?
Yeah, that's the thing. I'm trying to what we call start with the Blackboard, because I don't want to use a private web page or the one that is available free, because it might take a while for you to download it. At least if it's in the Blackboard, everything will be there. So I have no idea. We will have a group, a department meeting today. I will ask Dr. Timos about it, because usually at this time it is in the person above our salary grade. They told us it should be in 2 weeks. So this is already your 2nd week. So we're hoping that at least the areas will be by next week. Oh, 3 weeks? So
Also,
that means by next week, we might still have no Blackboard.
Also, can you ask him if he's going to post what he covered on there as well, the videos for his lectures?
With him?
Yeah, Dr. Demos's lectures.
Yeah, he should have recorded those things. I will ask him. Yeah, this afternoon.
I tried to press the record button while there was class going on, but it doesn't. It always says to ask the instructor for permission.
Okay, ask him for the recorded lecture.
Professor.
Yep.
How many credits we're gonna have for this class?
How many what?
Credits.
How many credit did they tell you? I think is it
the answer
the whole thing?
Is 3 credits for this course.
Yeah,
they set it up. They sent it in the email.
Yeah, they said it in the. I'm not the one, because I'm just one who said, okay, you prepared this one here. And
yeah, Professor Chang sent it out in the email when he attached the PDF of the so-called syllabus. So it's supposed to be 3 credits for this.
Because after today, my last meeting is doing chemical analysis. That will be on Tuesday. I'm hoping that the Blackboard will be available soon, so I can put all the materials there. Because as you could see, I think yesterday I emailed around 3 MB files. So it's not really good if you just send the thing. At least if you post it, it's easier for you to what we call download the material. And I'm going to make also available for those pure chemistry, the lectures that I have last summer for Gen Chem 1, and even during what we call the regular semester. What I'm trying to do is this: if ever we have our last meeting on Tuesday, that's not the last time that we're going to meet. Some of you can still ask help from me when you're starting your teaching, and I might ask also your help if we have some events that is related to chemistry for you to participate, because I'm in charge in some of the ACS activities, some sort of that. So this is just what we call the start of a community that we have. Okay, I don't know if you're okay with that, but for me, if you want it, it's fine. If not, it's okay. I'm not going to force you, but I'm more than willing to help all of you. I mean, not only after we're done here, until you establish your own teaching career. I think that's how you're going to what we call develop into a good teacher, if you're going to train yourself from time to time. Because I have a web page. I don't know if it's going to be useful with you. Project community. I can at least gather you here. So some of the materials that I just discussed is there, but the others, so this is just what we call some of the community service that I do, but I always do it in my country. So the materials that we have today is here. So the analogies here. So you will see the rhinoceros again there. Okay. So, and then right now I'm doing some webinars, but the webinars is from my countrymen in the Philippines, how they prepare for the new normal. So some of the stuff here, if you think it will be useful, there's some links of my webinars there, but unfortunately it's not pure English. I have some what we could use my language from time to time. But the thing that I want to do is, at least as we go on, I like to establish some sort of a community with the public school teacher doing sciences here in New York. This is for future purposes. Okay. So, question. So I'm still missing one student. You're supposed to be 15. I forgot what's the name that's missing. Sishan Halim. I don't know if it's with you during what we call demo session. Because right now you're only what, 14?
Professor, actually I think he doesn't have the links. He's not been getting any of the links.
But I emailed him.
He's also wasn't on the email list. He was confused, I think, as to whether or not he was in this class.
Oh. Well, she's the only one not accounted for. Everyone is accounted for.
Yeah, he is not on the email list that certainly Dr. Demos was sending, and I didn't check yours if he's on. If he's on,
maybe if he's not in Demos list, he's not also in my, because I just used Demos list also.
Yeah, he wasn't on there for some reason.
Yeah, I'll try to check and then maybe shoot him an email about the thing, because he's the only one that is not accounted for. Because I tried to look at the what we call the list. And Ilan, what's your field? You're the only one who have no field last time. I asked each of them to put.
Oh, my bad. It's biology.
Oh, sorry, biology. So the chemistry is still 5.
Although I did student teaching in chemistry.
Oh, you're also teaching chemistry? Because I asked them to what we could put what they're teaching. Most of them is biology or living environment. And I said, why did we develop this course if there's only less chemistry in this course? That's the thing.
I really appreciated your lecture today. Thank you.
Yeah. That's why when I learned that it is not all of your is chemistry, I try to change at the last minute the lecture. That's the thing. Because I said, if I'm going to put it all chemistry, then it will be what we call the non-chemistry might not like it. So I just try to incorporate it like a general thing. But unfortunately, since I'm chemistry will still be the center. So question. Any question? So I already gave the first requirement last time. You develop your own big ideas. Again, whatever your field, use that field. I'm not forcing you to become chemistry. Because if you're not chemistry, you might read some of the chemistry stuff. No, if you have your own field, I think each field has their own big ideas. You can find materials, but I want you to to develop your own, okay? Because the big idea started not in chemistry, but in science in 1970s. That's the start. They want to concentrate which ideas we're going to focus that is what we call beneficial to society. And then today, choose 2, okay, of the stuff that you have and develop your own material, again, in your own field. So I want it a material that you will really use in your class, because why waste time? Why waste preparing a material that you're not going to use. So it's just like hitting two birds with one stone. That's the one way I want the class to be done. And next meeting, you will also have to develop a material on your own based on the lecture that we have. So it's a little bit chemistry, but I try to incorporate it because the way that we're going to do is how do you do chemical analysis? How do you determine the stop, or what's the basis when you are going to go to your doctor, like what I'm going to do after our class here? So what's the basis? How do they know the sugar level? So what's the principle behind that? So we're going to discuss some of those stuff during our last meeting. So I hope you learned something. As I told you before, this is the first time that I taught this what we call class. I never taught a class like this before. Okay? So any question before we call it a week? Yes, Mona.
Can you hear me?
Yeah.
Okay. I am a little confused about what our first assignment was. Like,
Oh, the first thing that because by tomorrow I'm going to what we call write it. You develop your own big ideas in the field that you're teaching. So similar to the big ideas in chemistry that I have what we call tackle.
So like an essential idea to the study of chemistry?
Yep.
Like,
So
and how do we expand on that? Like, are we?
No, I mean, the way that you're going to do, you have the papers of the central ideas by Adkins and Gillespie, right? So you choose your own and then just put some short explanation. Why do you think that ideas is central or big or important? Because those big ideas are just the important ideas that they want to see that if you want to learn chemistry, this is the stuff that you need to teach. So for you, if you're teaching bio, if you want to teach bio, what are the ideas that you want your students to teach? So some sort of like that.
Did you want us to take one of the ideas from Atkins and Gillespie or expand?
No, you develop your own. You have your own list, right? Because at the end, if you can remember, I give you an example that I found in the net, in the web page, in the internet, about their own big idea. So it's your own idea. It's just that you gathered, I mean, you have different topics in your courses that you're teaching, right? So you're just going to choose, why do you think this certain topic is a big idea? You have to reason out why, some sort of that.
Okay, just a short explanation.
Yeah. Mm-hmm.
Okay, thank you.
Yeah. So any more?
Oh, and when are these assignments due?
That's the thing. I might email to you about this, what we call assignment tomorrow, because I'm hoping that the Blackboard will be available. So I'm still trying to what we call write it, but at least now I'm just telling you for each meeting, this is the stuff that you're going to need, because that's all the requirement that you're going to have from me.
Okay, thank you.
Yeah. Any more questions? So I think the temperature will be high again today. So stay safe. Have a nice weekend. See you on Tuesday. Okay?
Thank you,
How do
Professor.
they do it? in the Zoom meeting. Okay, see you next week.
Hey, Professor.
Yep.
Quick one. You probably just answered this right now, but I was a little distracted. Are you going to post the instructions for the assignments?
Yeah. I'm going to what we call maybe during the weekend, I'm going to what we call email you about the requirements. Okay?
All right, sounds good.
Don't worry.
Appreciate it.
Yep.
You have a good day.
You too.
Professor, so so far we have 2 assignments.
Yeah, so far we have 2 assignments. One is the big ideas, and then for today, give 2 examples or develop 2 strategies. Any of the strategies that I discussed that you can use when you teach. So you're going to what we call choose your topic on that.
Okay, thank you. Have a good one.